My name is Gordon Edwards. I'm a teacher of mathematics. I have been involved in this issue ever since the 1970s, very early 1970s. And Bob can introduce himself.
Hello, everybody. My name is Robert Del Tredici, and I'm a teacher of photography, the history of animated film, and drawing. I'm a visual person, but I've had a lot of experience in the nuclear field just because when the accident occurred at 3 Mile Island, I was mystified, horrified, and outraged. And from there, I went on to document the bomb. And my prime purpose of it was to make the whole thing visible. I did not approach it as a scientist, but as a visual person. But along the way, I picked up a lot of science. And Gordon and I have been working together to put together the science and the visuals in a way that will make the whole thing much more transparent than it is. While I was photographing the nuclear weapons industry and the nuclear power industry, I ran across other photographers who were doing similar things in this or that corner of it. So I decided to bring them all together, and we called ourselves the Atomic Photographers Guild. And everybody who was interested in it was doing it with the same passion, but doing a different corner of it. So there are 24 photographers that are together, and sometimes we have group shows and encourage each other to persist in this incredible endeavor of the human race, this nuclear age thing. I find it really important to make it visible.
Canada, as you may know, is the world's largest exporter of uranium and has always been so, really. We exported our uranium starting in the World War II atomic bomb project, and our uranium was used in the first 2 atomic bombs that were dropped on Japan, as well as in many thousands of nuclear weapons that were built afterwards. In fact, all uranium mined in Canada was sold for weapons purposes up until 1965, when our government then made a policy that our uranium would henceforth be sold ostensibly for peaceful purposes. It wasn't until 1970 that the Canadian Coalition for Nuclear Responsibility was born, and the Coalition for Nuclear Responsibility in Canada has really been organized with a view towards doing exactly what Bob has said, making the issues transparent both to the intellect and to the vision, so that people can better understand these issues and come to grips with them. We were asked to talk about the radioactive legacy of the nuclear age, and so we have organized this presentation in segments. The first segment has to do with fission products.
This is a model of a uranium atom that I photographed in the Museum of Science and Energy in Oak Ridge, Tennessee. Uranium is the mother element of all nuclear technology, and it has a very unusual aspect to its nature.
Actually, uranium was discovered about 200 years ago and was named after the planet Uranus, which had been discovered around the same time. But it had no practical use until about 70 years ago, when scientists in Berlin discovered that it is the only element occurring in nature which can undergo a self-sustained chain reaction of nuclear fission.
This is a monument to the fissioned atom in the formerly closed city of Chelyabinsk, near the Russian Chelyabinsk reactor that made plutonium for the bomb. It's an interesting sculpture because it symbolizes the splitting of the atom and the power that comes when you split a uranium atom. This is Igor Kurchatov in front, the father of the Soviet bomb, and in back, 2 hemispheres split apart. And the waves around them symbolize the energy that comes out when you split an atom. And the 2 hemispheres that are left over, that fall to the ground or get carried away by the wind, are the broken pieces of uranium atom, or the fission products.
When a uranium atom splits, it can split in hundreds of different ways, and as a result, there are hundreds of different fission products. These are broken bits of uranium atoms. They include things you've heard of, like cesium-137, krypton-85, iodine-131, strontium-90, and the list goes on and on. We have on our website 211 of these posted, and that's by no means a complete list. So we're talking here about hundreds of different chemical elements, all with their own individual chemical and biological properties, being created at the moment of the fissioning of the atom. When trillions of these atoms are fissioned almost simultaneously, we have the power of the atomic bomb.
This is a nuclear weapons designer. His name is John Hopkins, no relation to the university, at the Los Alamos Nuclear Weapons Laboratory. And he was showing me these images, and he introduced them to me by saying, these are just some pretty pictures from the early days. And when I asked him about nuclear testing, he was intimately involved in the tests at the Nevada test site. He told me a nuclear explosion is so interesting that really there's never an end to nuclear testing. We should test nuclear weapons indefinitely.
We see in these clouds, of course, the main mechanism by which those fission products get disseminated into the environment following an atmospheric atomic bomb test. Those bits, those fragments of uranium atoms circulate and carry over very long distances. Strangely enough, in Canada, the population that got the heaviest dose of fallout radiation from these bomb tests were the Inuit, living up traditional lifestyles in the Northwest Territories because of the particular susceptibility of the caribou who eat the lichen. And it's a very short food chain which concentrates the radioactivity very much. But these fission products not only go into the local environment, but also go high into the stratosphere, and they're still coming down year after year today. Nowadays, they call it part of the quote-unquote natural background radiation. There's nothing natural about this.
This is a man named John Smitherman, who is part of a group of 250,000 soldiers known as atomic veterans, because they were forced to observe at very close range nuclear weapons testing, because the government wanted to see what effect, physical or psychological, would happen to soldiers involved in a nuclear war. He was involved in the Able Baker tests, the first nuclear explosions after Nagasaki. They happened in the Pacific. And his job, besides observing the explosion, was to swab down the decks of the ships that were in the close range of the atomic explosion. He wore tennis shoes, short pants, and a T-shirt. And as he was washing down the deck after the explosion, he noticed at the far end of the ship a couple of men in moon suits with Geiger counters. And he thought that was very strange, because no one had told him that there was anything to worry about. As you can see from the photograph, his hand is swollen. He had multiple cancers. And what you cannot see in the photograph is that both of his legs at this time had been amputated. So he was suffering severe illnesses from the radiation exposure that he had received years earlier.
And Bob said that the military were interested in finding out the effects on the soldiers. This did not mean these kind of effects. They were not interested in these kind of effects. They wanted to know whether they could still fight. And in fact, they sometimes call these people atomic guinea pigs, but they were not. Had they been guinea pigs, they would have been followed closely and studied. They were instead forgotten and ignored because nobody wanted to know what happened to them afterwards. It is, of course, a feature of exposure to radiation that the damage is at the cellular level, and so that you can have 10, 15, 20 years later abnormal growths of cells which have been damaged years earlier by the exposure to ionizing radiation, as in this case. In general, because we're dealing with we're dealing with material particles. We're dealing with material substances, hundreds of them, and they all have their own chemical and biological properties. They go to different parts of the body depending upon what our body thinks they are. When our body is exposed to cesium-137, it thinks that it's similar to potassium and therefore puts it into the meat. When it absorbs strontium-90, it treats it as if it was ordinary calcium and puts it into the bones and the teeth and into mother's milk. When we get iodine-131 in our diet or breathe it into our lungs, the body puts it into the thyroid gland because that's where iodine normally goes of a non-radioactive variety. And that's where the damage is done. Inside, these become internal emitters. And many people fail to understand the difference between a brief exposure to external penetrating radiation and a prolonged body burden of materials which have been incorporated right into your digestive system. This is the face of a CANDU reactor. Bob took this picture while it was still under construction, and as a result, the man standing in front there was in no danger. There was no real penetrating radiation taking place here. Even when the uranium fuel bundles are put into the reactor, they do not give off much penetrating radiation, and it's quite safe to handle these fuel bundles for a short period of time. Once they go into the reactor, however, they undergo fission, and the same inventory of fission products builds up inside the core of the reactor.
What we want to make with the link with this image of a nuclear reactor is that the fissioning is the same. It happens much more slowly in a nuclear reactor than in a bomb. In a bomb, it happens all at once, and here it's moderated, it's controlled, it's slowed down, but it's still going after that release of energy that happens when those atoms split. In the case of a reactor, that release of energy boils water. In the case of a bomb, it kills 200,000 people in an instant.
What many people don't realize is that the radioactivity, the radioactive inventory of fission products in the core of the reactor is so intense that even after the reactor is completely shut off and the fissioning stops altogether, the core of the reactor still generates 7% of full power heat. And that's quite sufficient to melt the entire core of the reactor at a temperature of over 5,000 degrees Fahrenheit. Consequently, in August of this past year, when the Swedish reactor failed to be able to pump the water through the core of the reactor, there was a real danger of a meltdown. Had the core of the reactor become uncovered, as it happened at 3 Mile Island, the fuel would have spontaneously melted and released enormous amounts of these fission products into the atmosphere. That did not happen, but it was a scary incident.
This man's name is Bjarne Paulsen, and he was dragooned into helping clean up a nuclear accident at the Chalk River reactor. And he, as a result, inhaled and was exposed to all kinds of particles from the burnt fuel that came out from that accident. And he contracted many cancers, and took years and years for him to get the government to acknowledge, number one, that he was even present at the accident, and number two, that he had cancer.
Here again, we have an incident which dramatizes the dangers of the irradiated fuel. His exposure and the exposure of 600 other military men who were ordered to go and mop up the radiation following this accident, it was all due to a segment of spent fuel about this long, which broke off while it was being extracted from the reactor and caught fire because of the intense heat from the fission products. And in the process of burning, it spread fission products throughout the interior of the reactor in the form of a fine smoke. Think of cigarette smoke. And this material stays airborne for weeks and months after the accident and only slowly attaches itself, almost like plating, onto metallic surfaces. And it becomes, they had men scrubbing for day after day after day to try and scrub off the contamination. They reduced it a bit, but it's impossible to scrub it off. The contamination is so intense that it's just locked onto the surface.
This is a photograph of reindeer in Swedish Lapland at the Harads Same Produktor. This is a result of the Chernobyl cloud having floated over northern Sweden and raining out. The main element was cesium, and it got absorbed by the lichen, and the reindeer eat the lichen. And so the cesium goes into their muscle tissue. And I heard they're killing the reindeer in Sweden because of the radiation. So I looked into it further. I found my way to this meat packing plant. And no, they're not killing the reindeer because of the radiation, but they are culling the reindeer herds as they always do and setting aside those whose body burden of radioactivity is too high for the standards for human consumption. So I spent 2 days going through this meat packing plant. It was very ordinary. And then at the very end, he said, "Oh, by the way, would you like to see the reindeer carcasses that we don't prepare for human consumption?" And I said, "Yeah." And that was the very shot that I had imagined in my mind before even going there. And there it is, a locker full of reindeer, too radioactive for human consumption because of the Chernobyl cloud, which happened anniversary just yesterday.
Recently, I did an internet search, and I found that there are still dozens of sheep farms in northern England and in Wales which are still not able to sell their sheep for human consumption due to contamination from cesium-137 for that accident, which happened thousands of kilometers away in the Chernobyl accident 20 years ago.
I asked the man who ran this plant, what happens to the reindeer meat, thinking that it would be incinerated or buried or something. He said, "Oh, we give it to the mink farm just down the road." And it didn't occur to me to ask him what happened to the mink and the mink shit. This is an empty spent fuel pool. The uranium fuel that has been used to boil water, once its job is done, is so radioactive that it has to be submerged in a pool like this for 7 to 10 years. And, they say that the product of a nuclear reactor is energy from boiling water. But that is such a brief moment in the life of this fuel. I think you could say that the true product of a nuclear reactor is spent fuel. It stays here for 7 to 10 years, and then it goes on. It has to be submerged under 14 feet of water, and the water has to be continuously circulated to keep that fuel cool.
In the Rasmussen report of 1974, which was the U.S. reactor safety study, they pointed out that after a discharge of spent fuel into the pool, that if there was a loss of coolant in the pool, the fuel in the pool would melt down. And you would have a meltdown accident in the pool spontaneously. Now, this is less likely to happen with Canadian reactor fuel because it is discharged gradually rather than all at once. And consequently, some of it would be a little cooler than others. But in general, it is true that if the water is drained, the fuel is going to overheat, there will be damage to the fuel, and there will be releases of radiation to the environment. This is a serious security threat because these spent fuel pools are not protected by the reactor domes and the very thick walls which they're constantly talking about in terms of the reactor itself. They're much less protected than the reactor itself.
So the legacy of nuclear fission, the legacy of that part of the nuclear age, can be summarized as the spent fuel. After it comes out of the pool, after 10 years of cooling down, it can go into dry storage. It's put into casks, which are themselves heavily shielded and cooled, and it has to stay there for a decade or so before they decide what to do next. It can stay there for a long time, or it can go into another deep underground place. That's one of the other scenarios they're thinking of. This is dry cask storage in Quebec.
Here in Sweden, there is no dry storage, I understand. It's all wet storage under pools. Some of it, even the old fuel, is being stored under pools. But many countries, the United States certainly and Canada, have moved towards this dry storage as being cheaper. It's important to realize that this fuel is still quite hot, and it has air cooling and conductive cooling, and it still would be inappropriate to bury this waste deep underground because there would be no air circulation, there would be no way to dissipate the heat. So in fact, the Nuclear Waste Management Organization in Canada has recommended waiting for 30 years from ejection from the reactor before even thinking about deeper burial, which is what they advocate.
And here is the last scenario, or one of the next scenarios that they've come to as to what to do with the nuclear fuel. This is a test shaft dug in the pre-Cambrian granite of Manitoba, Canada, a quarter of a mile deep into the Canadian Shield, for checking out the possibility of storing this waste irretrievably deep underground.
Now, the difficulty is that even underground, it continues to generate heat. This is an Atomic Energy of Canada limited document, part of an environmental impact statement. After 70 years, the red indicates the heat generated by the buried irradiated fuel. This is the temperature distribution of the rock strata after 4,400 years as a result of that heat. Here we have the distribution of temperatures after 8,800 years, and according to the scenario that AECL calculates mathematically, they expect that the temperature of the surrounding rock would return to its ambient temperatures after 50,000 years. This is simply illustrating one aspect of what makes burial of nuclear waste difficult. This is not inert material. It is active material. It is radioactive. It is thermally active. It is physically active. It is chemically active. Ionizing radiation creates ions. So that any water, and this will be flooded with water, there's no doubt about that. Any water that goes in there is ionized, and any ionization, of course, increases any chemical reactions that are going to take place. You also have the shaft go into the rock, which disturbs the geological formation which was there. No scientist knows how to restore the shaft to the integrity of the original rock. When you think of the pyramids of Egypt, 5,000 years old, 50,000 years is 10 times that. So we're talking about really man-made structures which are going to withstand all these geological and other forces over a period of time which dwarfs the recorded history of mankind. Some people are slightly dubious of whether we actually know that this is a good thing to do. And many people have some people at least, have come to the conclusion that it would be irresponsible to put this material out of the control of humans. Here we have a graph which is a little difficult to interpret, but if we just look at the top line, this is toxicity of irradiated fuel coming out of a Candu reactor. One Candu reactor, only 1 year's worth. The amount of water needed to dilute this waste to so-called safe drinking levels is equivalent to the volume of water in Lake Superior, the largest of the Great Lakes. Over time, it declines in toxicity for the first 100,000 years, and then it increases in toxicity again. After 10 million years, it's actually, this scale, the scale of time, runs up to 10 million years here. After 10 million years, it's actually more toxic than it is after 100,000 years. And that's because of internal changes that are taking place. Among these hundreds of materials are some that are very long-lived, and they're continuously transforming themselves into other materials through radioactive decay, some of which are more toxic than the original. It just gives you some idea of the complexity of the task that we are trying to say that we know the solution to.
This is the second legacy of the nuclear age that we're going to deal with today. The first being fission, and the second, natural decay of uranium. So we're talking about dealing with uranium in its natural state in uranium mining, pulling it out of the ground. The first uranium mine in the world was at Port Radium in the Northwest Territories, just underneath the Arctic Circle. And that's where I got this shot of one of the Dene Indian men who lived up there, and the men were hired to haul uranium from the mine in sacks and carry it on their shoulders, put it onto barges, sleep on the sacks as the barge made its slow way across Great Bear Lake, one of the largest freshwater bodies on the planet. They're holding up a government warning published in 1931, the text of which is on the board back there. Here's the text of it here that indicates that the government knew full well that it was hazardous to handle radioactive substances. And they published this warning for their own people in Ottawa who are handling samples of uranium ore and its byproducts. And they were saying that ingestion of small amounts of radioactive dust or emanation over a long period of time will cause a buildup of radioactive material in the body, which eventually may have serious consequences. Lung cancer, bone necrosis, and rapid anemia are possible diseases due to deposition of radioactive substances in the body.
And what's interesting about this is that we're often told that they didn't really know the dangers back then. This is complete poppycock. The dangers of radiation and being exposed internally to radioactive materials was well documented as early as the 1920s. And in fact, the reason why this warning could be issued in 1931 is because there was already a wealth of information as to the biological hazards of radiation. In fact, when they talk about radium, Those miners that we saw earlier, the Dene Satu of Great Bear Lake, they had actually started off mining radium, which is one of the uranium decay products. You know, uranium is a weird substance because it transforms itself into hundreds of different forms. When it's fissioned, as we already mentioned, you get these hundreds of fission products, all of which, in a certain sense, are just broken pieces of uranium. They're descendants of uranium from a violent process of splitting. Radium and radon gas and other materials such as that are slower products of uranium, decay products that just take place naturally in the ground. These women were hired to paint dials to make them glow in the dark, and in the process they got minute amounts of radium into their body. They developed a host of illnesses. Some of them died rapidly from rapid anemia, so bad that they just perished. Others died from bone cancer within 5 to 10 years of exposure. And still later, 15 to 20 years later, the survivors, many of them developed head cancers, cancers of the sinuses, cancers of the mastoid. The price in the 1920s was $100,000 per gram, the most valuable substance on Earth. By the outbreak of World War II, it had dropped to being virtually worthless because there was no market for it. It had killed too many people. And now it is discarded as one of the waste products from uranium mining and left to the environment. Well, they don't throw it into the environment, but the trouble is, who's going to keep it out?
This is a photograph of Bernard Benally, a Navajo uranium miner near Shiprock, Arizona. He worked in the mines like many of his community, and some years after he retired, he developed lung cancer from inhaling the radon gas in the mines.
This is really what killed both the women who painted the dials and the miners who breathed the radon gas. It's called alpha radiation.
They say that radiation is invisible, but this tells you that you can see it. It's called an autoradiograph. What they do is they coat a tissue that has a particle of uranium, a particle of radiation in it, radioactivity. This is a particle of plutonium. They coat it with an emulsion, and the emulsion reacts like photographic film to any burst of energy. Alpha particles send out occasional blips of energy, and this is, you see the little black lines. That's how many bursts of alpha energy are given off over a 48-hour period.
I would like to mention here that alpha radiation is harmless outside the body. It can't penetrate through a sheet of paper. And sometimes people are given the misleading impression is that therefore it's nothing to worry about. On the contrary, all scientific studies show that inside the body it is at least 20 times more damaging than other types of radiation, the more penetrating types like gamma radiation, X-rays, and beta rays even. These things are very, very damaging once they come in contact with living cells, which can only happen if it's inhaled, ingested, or absorbed through the skin or through a cut.
This is a wall of uranium mill tailings thrown out of the mill after the uranium ore has been processed and turned into yellow cake. These are the leftovers. The uranium is mostly taken out of it, but what's left behind are all the decay products of the uranium. So there's still a tremendous amount of radioactivity in here. This is in Ontario, and as you can see, it's carried away by the water, the rain, and the wind. Behind that wall,
if you drive up the road, which you cannot see on the right-hand side, it's an entire lake full of this radioactive sand. This particular deposit is 70 million tons. And why is it radioactive? You would think that if they mine uranium and take the uranium away, that what's left would be non-radioactive. But on the contrary, it's more radioactive than the uranium that is extracted. The reason is because uranium itself in the ground decays into thorium-234, which itself is radioactive. That turns into protactinium-234, which is again radioactive. And we have this whole decay chain. It turns out that when you have old uranium which has lain in the ground for billions of years, all of these materials are equal in radioactivity. However much uranium there is exactly that amount of radioactivity of all the others as well. We have here the radium, which killed the dial painters. We have here the radon, which killed the miners. We have here the polonium-210, which killed that Russian spy Litvinenko. These are among the most dangerous radioactive materials known to science. They have been identified as particularly dangerous. The British Columbia Medical Association describes radium as a superb carcinogen. People who've studied polonium-210 have pointed out that it is literally billions of times more toxic than cyanide, and that a particle the size of a grain of sugar would be enough to kill 1,000 men the way Litvinenko was killed. This is the material which is discarded when we mine uranium. It's dangerous stuff. The third radioactive legacy of the nuclear age is depleted uranium, which is a cast-off form of uranium. And it turns out to be, although of no interest or use of a civilian nature, it turns out to be very interesting to non-civilians.
Depleted uranium comes from a uranium enrichment plant. It's the other end of the word enrichment. After the uranium has been passed through the thousands of filters in gaseous form to separate the uranium-235 from the uranium-238 in order to use it for the bomb program, the 238 is the depleted stuff.
This is the field of depleted uranium cylinders, which are really just cast-off uranium, and you would think, judging from the fact that Canada says keep it, we don't want it, it becomes American property if it's not claimed within a few months, and Canada almost never claims it.
What Canada does is it sends its uranium to the United States where they have these huge enrichment plants. They don't have those plants in Canada. So even if they want to enrich it just ever so slightly for nuclear reactor fuel, they still leave behind the depleted uranium.
Now, this depleted uranium is the result of the preparation of civilian fuel for civilian reactors. In other words, it is a civilian waste byproduct. It really is a radioactive waste, but it's not considered a waste by everybody. What is uranium enrichment? As Bob mentioned, there's two types of uranium in nature. U-235 is the kind that fissions and releases energy, and in order to make it useful, we have to increase the concentration of U-235. When we have more U-235 and less U-238, that's called enriched uranium. The opposite, more U-238 and less U-235, is called depleted uranium. Even though this is a waste byproduct, look what they do with it.
These are uranium ingots weighing 1 ton each. Uranium is very heavy metal, and they are being prepared to be inserted into this uranium extrusion press in Ashtabula, Ohio, where they are hit with tremendous force and turned into small, narrow pipes, hollow pipes. These pipes are then inserted into a reactor, bombarded with neutrons, and when they absorb neutrons, depleted uranium atoms are turned into plutonium for the bomb. This is the Nagasaki bomb, the plutonium bomb, that has become the bomb of choice in modern nuclear arsenal.
Most people don't know that for decades, all of the plutonium and all of the warheads, not only in the U.S. nuclear arsenal but in others, have been fabricated directly from U-238, which is cast-off depleted uranium. That's what happens with U-238. It doesn't fission, but it absorbs a neutron and becomes U-239, which then disintegrates rapidly into plutonium-239 and creates an element man-made, heavier than uranium, the first real transuranic element.
This is a model of a modern hydrogen bomb warhead. You can see the ball of plutonium in the center of that soccer-shaped sphere on the top.
And that plutonium bomb is really for the purpose of raising the temperature to 50 million degrees, because that's what you need to ignite this fusion reaction, which takes place in the center. But there's a third phase. The third phase, it's called a fission, fusion, fission bomb, a 3-stage nuclear weapon. And the third stage is, guess what? Pure depleted uranium. The depleted uranium provides more than between 2 and 10 times of the power of the fusion reaction is obtained by the fissioning of U-238, which only happens in a fusion bomb because the neutrons are so extraordinarily energetic that in this case they can actually split the U-238 atoms. So this depleted uranium turns out to be mighty useful.
There's another use. It didn't used to be commercially a viable product, good only for turning into plutonium. But, as we all have heard, it gets turned into depleted uranium munitions because uranium metal is so dense it can cut through standard metal in a tank like a knife through butter.
Now, it not only cuts through, but it also burns through. This depleted uranium penetrator is metallic. It's uranium metal, and it's pyrophoric. If you know how phosphorus burns, or if you know how sodium burns with a very intense energy, depleted uranium burns with an even more intense energy, and it literally burns its way through, as well as penetrating through sheer force. And this creates a kind of a smoke. Think of cigarette smoke, secondhand cigarette smoke, except this is secondhand uranium smoke. And it's very dangerous because it's so easily inhaled into the lungs. It's the alpha radiation again. Once that gets into your lungs, it can do a lot of damage. Hence, we have the contradiction that depleted uranium munitions are safe, when they're not used, but as soon as they're used, they become extremely dangerous because they turned into a gaseous form, a smoke form. These are men in the American desert, all suited up and totally protected, examining a tank that's been destroyed by a depleted uranium shell. Notice how protected they are, but the soldiers are told they need no protection.
And now the fourth legacy of the nuclear age, the plutonium economy.
Plutonium is yet another transformed version of uranium.
This picture shows a glass paperweight. The interesting thing about it is the size. It was machined to match exactly the size of the amount of plutonium in the Nagasaki bomb. Now, that was a very early bomb, and at that time, although it destroyed the city of Nagasaki, they did not know how to contain the fissioning plutonium long enough for all of it to fission. So the force that destroyed Nagasaki was 1 penny's worth of plutonium. The rest was just blown to the winds.
They can now get the same power of explosion with half as much plutonium.
This is a glove box for the handling of plutonium, photograph taken in the plutonium finishing plant at Hanford, Washington State. And it's a sealed environment. It has to be kept under negative pressure, filled with an inert gas so that the plutonium does not catch fire like it has a tendency to do in open air.
Also, the woman is carefully suited up because although it is an alpha emitter and therefore safe to handle, the tiniest speck inhaled into the lungs or absorbed onto the skin could be very fatal for a person who ingests that material or breathes it into their lungs. Consequently, the glove box apparatus. Bob, at the risk of his own life, must have been inside this glove box in order to take this picture. But he tells me he wasn't.
There was another window on the other side. This is the Windscale reprocessing plant in Cumbria, England. The way to get plutonium out of the spent fuel is to reprocess it. You chop up the fuel and you dissolve it in boiling acid and plate out the plutonium, and you are left with the richest brew of corrosive, highly radioactive, liquid, high-level waste. And at the back end of the Windscale plant are these pipes that go out several miles into the Irish Sea and discharge plutonium-contaminated and other radioactive liquid wastes into the Irish Sea. They've been doing that for over 30 years, and as a result, the Irish Sea has become the most radioactive body of water on the planet. When they tell you that nuclear energy is clean and safe, you should maybe consider asking the fish in the Irish Sea and the people who eat those fish.
Now, you may say, well, wait a minute, isn't this military, bombs, reprocessing plant, weapons? Well, not really, because the nuclear industry realizes that if they really are successful in having a nuclear renaissance, if they really are successful in getting tens of thousands of reactors built worldwide, they will have to use plutonium as a fuel. This is why countries that have heavy investments in nuclear power, such as France, USSR, Britain, Japan, India, they all have reprocessing in place. And this is not for bombs necessarily, although it could be, but it's for civilian fuel, to recycle and recapture that plutonium to use it as a fuel. When you hear the word MOX, think plutonium. MOX is a code word for plutonium.
That liquid waste, highly corrosive acid mix is one of the most difficult wastes to handle, and it's stored here at Hanford in these double-wall carbon steel tanks. These tanks are replacing earlier single-wall tanks that leaked because the acid ate their way through it and leaked 500,000 gallons of high-level waste into the soil around Hanford. So now they're building a whole new set of tanks, doubling the strength of the walls, and the tanks have an expected lifespan of 50 years.
The nuclear authorities have said that they can't dig up the waste which is leaked into the soil because it would be far too dangerous for the workers and for the environment. Upsetting this material by trying to dig it up might be worse than leaving it where it is. They're carefully monitoring it and watching how it's moving, but they really can't do anything about it other than to observe.
And it's right next to the Columbia River. Not a good place for high-level liquid waste underground storage. This photograph was taken in the village of Muslimovo in Chelyabinsk, 35 kilometers downstream from the Chelyabinsk reactor that made the plutonium for the first Soviet bombs. The Soviets were in a great hurry to catch up with the American bomb program, and so they dumped their high-level liquid waste straight into the Techa River. The water turned black. Many people up and down the river fell ill. Nobody told them what was happening. They just said, don't use the river anymore. They'd been using it for centuries. And in this photograph, Western activists were visiting Muslimovo and Chelyabinsk and measuring the radiation in the silt and in the water that goes past their town. So these women are finding out for the first time now, 40 years after the fact, what was happening, what happened to the river and what is happening with the health of their community.
Here we have a display of all the nuclear weapons in the U.S. arsenal at the end of the Cold War. It's just a miniaturized model, but it's a pretty impressive sight. When you think of this as representing vertical proliferation of nuclear weapons, and you think about the prospect of horizontal proliferation to countries and subnational groups around the world, which would be facilitated by the commercialization of plutonium. The thing about plutonium is that you can take plutonium from MOX fuel or from any other form, and by extracting it chemically, and remember, being an alpha emitter, it's not that difficult to handle. You don't need heavy shielding. But to extract the plutonium from that means that you can make atomic bombs from that MOX fuel. This cannot be done with ordinary low-enriched uranium fuel. Nobody can make a bomb from that. The enrichment is simply not high enough. Plutonium is a different kettle of fish altogether.
This is a photograph of a nuclear weapons designer named Ted Taylor, who realized that we shouldn't be making our bombs bigger and bigger. The wave of the future is to make the bombs smaller so we can actually use them. And he invented the smallest nuclear weapon in the American arsenal, nicknamed the Davy Crockett. He also worked on some of the biggest ones. Ted Taylor, however, when he realized the consequences of nuclear war, became a changed man. He spent the rest of his life, many years, talking, number one, nuclear weapons are a horrible addiction, and they must be treated like an addiction. And that the number one danger to the world is the proliferation of plutonium.
And he meant plutonium through civilian nuclear power. He said that the number one problem is the spread of civilian nuclear power around the world, which is insidiously spreading the raw materials for making nuclear weapons. Bear in mind that the plutonium in the irradiated nuclear fuel, plutonium alone has a half-life of 24,000 years. So thousands of years after the reactor has been shut down and forgotten, thousands of years after all benefit has been obtained from this, future regimes can take the plutonium out of that spent fuel and make atomic bombs from it. We are literally sowing the seeds of our own destruction. And I think that this is a message which has got to get out into the larger community, because the nuclear industry has been very successful in couching the discussion about a nuclear renaissance in completely deceptive terms in terms of what the future holds in store if they are successful. And this brings me to the question of nuclear renaissance. Let me just run through a little imaginary scenario for you. Imagine one reactor pumping out irradiated fuel. After 2 years, each of those red dots indicates 1 year's worth of irradiated fuel, which would be what you saw in that chart of the toxicity over 10 million years. So here we have 2 years' worth, then 4 years' worth, 8 years' worth, 16 years' worth. Now the color has changed because it's beginning to cool off a little. You can now put it into dry storage. It's not quite as hot as it was for the first 10 years. Now we have 32 years, and it's cooling off more. It now might be able to be buried underground if you wanted to. And here's 40 years. So you see that it's an enormous threat at the surface of the Earth to have this irradiated fuel just waiting for something to happen to liberate these fission products and other poisons into the environment. So we need to have a solution to this problem, and the industry, through its ingenuity, has come up with a solution, which is geological disposal. The first 2 years, well, actually, no difference, because you can't bury this stuff, it's too hot. 4 years, well, still no difference. 8 years, oops, same thing. After 16 years, however, we begin to see progress. It might be possible, I don't think it is actually, but it might be possible to bury this portion. Hooray. The problem is that the 90% of the radioactivity is in the first portion, the red hot stuff. And therefore the catastrophe potential is virtually unchanged by burying the older fuel and leaving the fresh fuel in place. After 32 years, after 40 years, well, you know what? As long as these reactors keep operating, you're always going to have that 10 years worth sitting right there, and the catastrophe potential is going to be essentially unchanged. It's like the difference between getting rid of kiloton bombs but keeping the megaton bombs. And you say, well, the world is safer because we got rid of a few kiloton bombs. Well, as long as you got those megaton bombs, you're not doing much good. Same thing here. You get rid of the cold and old fuel, you're not doing the world much good if you're still keeping that hot stuff right there at the surface. Now, if you multiply the reactors, then, of course, this problem becomes multiplied. With 4 reactors, with 6 reactors, with 8 reactors, holy mackerel. You know what? Even with geological disposal working perfectly, as fast as it can possibly operate, we have an ever-growing inventory of unburied waste at the surface, which grows in strict proportion to the growth rate of the reactors themselves. We have not solved the problem. Now, the industry likes to say that it's a solution to the problem. They have another agenda in mind. They are smart enough to know that this is not a solution to the problem. What it is a solution to their own public relations problem. And it is also a solution to another problem, and that is, how do we fool the public into getting all the nuclear waste into one place so that we can then reprocess it and get the plutonium out? How do you pay for all the cost of transporting that material to one location in order to get that done? Well, in Canada, we had a Royal Commission report in 1978. It was entitled A Race Against Time, a very appropriate title, about nuclear power. And what they said is they recommended against centralized storage of any kind of irradiated nuclear fuel because they said, we believe that centralization implies reprocessing and the plutonium economy, and therefore centralization should be resisted and should not be recommended.
Rolling stewardship. This is what we hope to be the beginning of another legacy of the nuclear age. It's a concept that I became familiar with as I was asked by the Department of Energy to document the cleanup of the nuclear weapons factories. Because of my early work, which I did completely on my own at work in the fields of the bomb, when Hazel O'Leary became the head of the Department of Energy, she hired all kinds of people who had been suing the Department of Energy and winning their lawsuits. And she hired them because she said, these people really know what they're doing. One of those people I met on a trip to Russia when I went to Chelyabinsk. His name was Jim Werner. And he had just decided to take a chance. He was asked to work for the Department of Energy to help clean up everything. And he knew that Hazel O'Leary was really meant what she said. So he told me, Bob, we're going to do some books together. Now, normally, a government book, the subliminal message of it is, trust us, we know what we're doing. But he said, Bob, he said, this problem is so hideous that that's not going to be the message. The message should be, this is way bigger than anybody imagined, and we don't really know what to do about it. So I signed on board, and for several years I was able to go to all kinds of different sites. And I learned that when I visited one site after another and talked to the technicians there, they were quite amazed that I had been to different sites because they don't get to see them. Here's a shot taken at Los Alamos. It's transuranic waste contaminated with plutonium. And there's an owl there, not because they are so wise about handling their waste, but because the owl is meant to scare away rats and birds who will nest in the waste and burrow into it and possibly create a way for that to get into the environment. What is rolling stewardship? Rolling stewardship is a concept that takes into account the fact that we do not really know what we're doing. Here are some of the things I saw when I visited the site, some very unusual things. This trench, they look like barrels, but if you go in for a closer look at them, you'll see they're enormous structures. They are the hulls of nuclear submarines. What happens to a nuclear reactor that propels a submarine? They take the fuel out of it, put it somewhere else, but the reactor itself is still highly radioactive, all kinds of fission products and activation products, and they bury them in the hull in these trenches. Those trenches can take 100 of these hulls, and then the trench is covered with clay. Here's another site I saw. This is low-level waste, stored for many years in this method of these 4x6 steel boxes, and they put it into the ground and they bury it. That trench there, they're going to cover it with dirt, is the last trench that they used this method for, because they decided they had a new method, which was, next slide please. Now this man is looking at the alternative way. This is in the Savannah River plant, South Carolina, where they make plutonium for the bomb. They have 5 plutonium reactors there. They're now going to say, okay, we're done with trench burial. Let's put it into these vaults now. This is a whole new method, and it'll be safer for 300 years more than the trenches were safer. But, of course, the waste itself is still problematic for millennia. Next slide, please. This is a safety sign at the Hanford Plutonium Finishing Plant. Stop. Take 2 seconds. Safety thought. It's important. It's important to think about safety. But the trouble with the whole handling of this issue of nuclear waste and its legacy is that all the solutions are short-term. Nobody's really thinking long-term. And that's where rolling stewardship comes into effect. The rolling stewardship admits that, number one, this whole thing is a mess. Number 2, people don't really know what they're doing. And number 3, they're making it up as they go along. They're flying by the seat of their pants, trying all sorts of things, and then redoing it. Rolling stewardship begins by saying, we do not know what we are doing with this stuff. That's step number 1. It's not a solution, but it's a beginning of the sort of the basic ground level approach to this stuff. Rolling stewardship means you put it where you can see it, and you contain it as well as you can, and you roll it to the next generation in a pretty decent package so that they can do the next thing. And they can sit on it and watch it. They know where it is, and they've got it. They admit they don't know what to do with it, and they roll it forward. So you've got it where you can see it. It's a responsible approach. It's not a solution, but at least it's not being in a state of denial. And so that, to me, is the way to go. And that notion of rolling stewardship should become part of any debate on what to do with nuclear waste. And it's not. The whole phrase is relatively unknown. So keep it in mind and roll it out on the table next time you're talking to some people who are in a position to maybe think about it.
I think it's very important to realize what the nuclear industry is doing in its PR campaign for a nuclear renaissance. They are really trying to hypnotize people once again. I call it the nuclear relapse rather than the nuclear renaissance. They're trying to hypnotize people once again to think that this is a clean, safe technology when it is anything but. I think that it's very important to actually espouse in the environmental community something like rolling stewardship as a responsible management scheme, not a solution, because we have to frankly admit that we do not have solutions. And to pretend that we have solutions is irresponsible, and not only irresponsible, but criminal to future generations. As the great Hannes Alfvén, the Swedish Nobel Prize-winning physicist, said years ago, you cannot claim that a problem is solved simply by pointing to all the efforts that have been made to solve it. The fact is that we do not have any scientific principles which allow us to say that this is going to be safe for the next X thousand years. There is nothing in the scientific tradition or in the scientific lexicon or in the scientific arsenal of tools which allows us to reach such a conclusion. It is really ultimately based on making the sign of the cross and hoping for the best. And that is just not good enough. Thank you very much for your attention.
I'd like to ask a question. I understand the ethical position that you presented at the end about having a rolling stewardship oversight of the existing legacy wastes. But the problem that strikes me is that because that critical 16-year period where the spent fuel discharge from reactors is the most dangerous and therefore the most attractive to terrorists, if you store that above ground and monitor it, it can be seen, doesn't that make the target, the one that's going to be the most high-value target for a suicide terrorist group, if you fit that into your philosophy of above-ground monitored storage, which is what you're proposing?
We didn't actually, thank you. Did everybody hear the question? We didn't really talk specifically enough about the concept that the logic of rolling stewardship by itself implies phase-out. Because the reason they want to talk about geological disposal is so they can say that the problem is solved and therefore we can continue to expand the nuclear industry indefinitely by putting the waste out of sight and out of mind. At the present time, there's no way that they can bury this 16-year-old waste because it's too hot. So that terrorist threat that you're mentioning is really not resolved by anything the industry is proposing at the present time. On the other hand, a nuclear phase-out and shutting down these reactors would, in fact, gradually reduce that risk by getting that red-hot stuff, which is the most volatile, which is most susceptible to releasing gases, fission products in a vapor form, and so on, by getting that stuff to cool off so that 10 years after shutdown, you already have a significantly safer situation. By no means nothing to be complacent about, but a lot safer than what you've got right now. So it's important to realize that implicit in what we said, and it should have been more explicit, is that simply the logic of the arithmetic dictates nuclear phase-out as the only responsible approach. If you look at what I was showing with regard to the accumulation at the surface of that red-hot fuel, the only thing that would make any disposal scheme feasible, let alone practicable, would be phase-out. Because if you're not phasing it out, you're always going to have the same or a magnified catastrophe potential at the surface where the reactors are located. You haven't resolved that problem in any substantial manner. You've reduced it marginally, but only marginally. If the environmental movement were to push for rolling stewardship, it would give them also a very strong argument for phase-out. And by the way, just one final comment. Not to disagree with you on the terrorist target of the red-hot stuff, but I might point out that the really old stuff is a terrorist target in a different sense. Because the older it is, the more accessible the plutonium is. And that's another problem. That's a very serious long-term problem as well. We don't have any answers to that, but boy, that's a big one.
And it will take a lot more than a suicide bomber to get that plutonium out of the hot fuel.